Let's continue reviewing our double integrals. From double integrals 1, we had this region bounded by the lines x equals 2, y equals 4, and the parabola y equals 4 minus x squared. So if we want, we can find the area of the region just by finding the area under the parabola and then subtracting that from 8, the area under y equals 4. So we're going to build a double integral, and if we want to make sure our answer is correct, we could just evaluate the double integral to make sure our area is correct. So let's describe this region for a double integral. So first we want to notice our left and right, and our right and left and right, and our bottom and top. So when x is constant, x will go from 0 to x equals 2. And when y is constant, y will go from 0 to y equals 4. So we have what the outer integral is going to be, or the last integral is going to look like. In the dy dx integral, when x is last, we'll go from 0 to 2. In the dx dy integral, when y is last, we'll go from 0 to 4. So to integrate some function, as usual, we want to write 2 double integrals, because why do one problem when we can do, or why do each problem once when we can do each problem twice? Nothing beats a 2-for-1 deal. Close enough. You are receiving problems, so there. So in the dy dx integral, x is last, so x is the easiest thing to write down. We'll go x goes from 0 to 2. For a typical x value, we write what y is between. So for this typical x value, the region starts off at the parabola and goes up to the line y equals 4. So y starts at the parabola and goes up to the line y equals 4. When we write the integral from 4 minus x squared to 4, y equals 4 minus x squared to 4, we're saying the bottom is the parabola, the top is the line. The bottom is the parabola, the top is the line. And so those are our bounds on y. If we want to make sure that this is correct, we can integrate the function 1 dy dx, and that will give us what we're looking for. If we think about what we would do in calculus 1 to find this area, the function we would integrate from 0 to 2 is the top 4 minus the bottom 4 minus x squared. When we integrate the function 1, that's what we would be integrating. So the next step in the dy dx integral is the dx integral that we would set up way back in Calc 1. We want to be able to set things up both directions. So in the second double integral, we want to set up a dx dy. The constant stuff is easiest to do. Y goes from 0 to 4. The bottom is 0 and the top is 4. The x goes from left to right. At a typical y value, the left is the parabola and the right side is the line. At this point, we're going to have to turn the function around, because the function says y equals 4 minus x squared, and we need to solve for x. So x will start off at the parabola and end at the line. So in this case, the right is the line, and then the left is the parabola. So if y is equal to 4 minus x squared, then x squared is 4 minus y. And so x is plus or minus the square roots of 4 minus y. Since we're on the place, we're in the quadrant where x is positive, we want the positive square roots of 4 minus y. The x integral just goes from left to right. The y integral goes from the bottom to the top. This one will not integrate to the function that we're familiar with, because we set up integrals for area in Calc 1 as dx integral. But if we read the problem sideways, the top is the 2 and the bottom is the square root of 4 minus y. Any questions? The other problem on this quiz, we would integrate the other region, in which case it would just change the roles of the line, or the axis is on the left, the parabola is on the right, the axis is on the bottom, the parabola is on top. So we'll just change up which expression, the order of the expressions show up. We'll integrate. If you integrate f at xy equals 1, that will give you the area of the region. And you can check that area using Calc 1 style techniques. Questions? Is everybody okay? Y'all look super stoked. You look like this.
Today it's not very good. How do you less than 8,000 to see?
Constantly. All right. From double integrals 2, we have this this function 6x minus x squared. We have a different parabola. In this case, we're going to have both sides of the parabola, the left side and the right side. And so that's going to give us some trouble when, or not really that much trouble. That's going to give us some problems when we try to turn this into to solve for x. So first things first, we should know what x is between. And we should know what y is between. In this case, we have a parabola and we have x-intercepts at 0 and 6. So knowing what we know about parabolas, we know that the vertex will be halfway between the x-intercepts. So the vertex happens when x is equal to 3. And if we plug in 3, we get, so y evaluated at 3 would be 6 times 3 minus 3 squared, 9. So that gives us that y is equal to 9. The vertex is at 9. The easy integral to set up is just the one that ends in dx, because that makes it in the first iteration in our double integral will send us to a dx integral, and we know what that one should look like. We should just integrate from 0 to 6, the 6x minus x squared. What that looks like as a double integral. Y goes from, for a typical x value, y goes from the origin, or sorry, the x-axis up to the parabola. So y starts at 0 and ends at the parabola. Then x goes from 0 to 6. What we notice about this integral is that the first iteration in the double integral, the first step in the double integral, will take us to the dx integral that we expect way back in Calc 1. So this one is the time machine back to Calc 1. So this one is the time machine back to the Calc 1 dx integral. The dx dy integral requires us to describe the two sides of the parabola. And that means we need the two different functions. In this case, the bottom was the x-axis and then the top was the parabola. But when we integrate the other direction, the y part is easy. We'll go from 0 to 9. The y part is easy. We'll go from 0 to 9. But on the x part, for the x, we're going from the left side of the parabola to the right side of the parabola. So the left is the parabola. And the right is the parabola. The problem here is that both sides are the same parabola. The best way to deal with this is to not use the standard form 6x minus x squared. That's really good for finding the intercepts, really bad for dealing with things like the vertex or solving for x. So I would rather write this in vertex form and say y is equal to 9 minus x minus 3 squared. So a better form for this parabola would be the vertex form. The reason is that this form only has one instance of the variable x, and we can more easily invert to solve for x. So here we're going to use the vertex form to solve for x. So if we write y is equal to 9 minus x minus 3 squared, then x minus 3 squared is 9 minus y. So x minus 3 is plus or minus the square root of 9 minus y. So x is 3 plus or minus the square root of 9 minus y. So here's the vertex form of that parabola. There's the x coordinate of the vertex is the 3. The y coordinate of the vertex is the 9. That shows us that in the middle is the 3, and then plus or minus is the symmetry on either side of the axis of symmetry of 3. In this case, the 3 minus the square root, that's the left side of the parabola. 3 plus the square root is the right side of the parabola. We needed the two different functions that represent this parabola, the left side and the right side. In the middle is the 3, and it's the same amount, plus or minus. That's the same amount on either side. That's the symmetry of the parabola. That same amount on the left and right, that's the symmetry of the parabola. Any questions? Yes. So that is a great question. Could we just go from 0 to 3 and then double it? If the only question we care about is finding the area of the region, then yeah, because we know the symmetry tells us it's the same area on the left and the right. The reason that we want to be able to we'll want to be able to set up the entire double integral is if I do something like vary the density of the region from left to right. If I vary the density like we did in the variable density problems, then the mass on the left is not going to be the same as the mass on the right. Now, if I vary the density only up and down, it won't matter if we split it left to right. But if the density varies at all from left to right, if the density, for example, is a function in any way of x, then we won't be able to just double up the area. Does that make sense? So we want to be able to, although there are a lot of workarounds for how to get at certain things like area, we have to be careful that we're not just restricting or limiting ourselves in how we use the tools that we have. Questions? That was such a perfectly timed question. You all should be wondering whether I planted that. I'm like, I'll pull the student aside. I'm like, hey, ask this question after I do the second problem. All right.
Control audience.
An audience plans. Any questions? How's everybody okay?
Just gotta remember that step. That's the one.
Yep, then there's that. How's everybody okay? Everybody looks so stoked. So if f of xy doesn't actually depend on x, then we can just look at the left half and double whatever we're counting. Even if I told you that the density varied with y, if the density was variable up and down, as long as our function f of xy doesn't have x at all, then we can just do half of it and double. If f of xy does not use x at all, does not. So more generally, if the function f of xy does not depend on x, then we can double what we get from 0 to 3 or from 3 to 6. But notice from 0 to 3, we have different values of x. than we have from 3 to 6. So it's symmetric, but here are different values of x. If we got different values if the function has different values when x is 2 than when x is 4, then we can't just double up what we get on 1/2.